Okay, so good morning. Hello, everyone. This is Giacomo speaking. My name is Giacomo Beccari. I am pleased on behalf of the ESO Office for Science and the Directorate for Science to welcome you all again to the third event of the ESO Cosmic Duologues. Thank you everyone for being again with us today. The topic of today is again one very big, one of the big arguments in the current currently in astrophysics and astronomy, which is the initial mass function. Of course, when one thinks of the initial mass function, basically is one of those concepts or that basically touch upon there is not a single field of astrophysics that is not somehow affected by our understanding of the initial mass function, and that's what we are gonna hear today about. I'm very pleased to welcome the two speakers of today that will help us in the duologue, which are Teresa Yerabkova and Andrew Hopkins. So let me just give you. So Teresa, she's a PhD student. I mean, she just finished the PhD. She submitted the thesis very recently. She wrote already a remarkable piece of work on the integrated galaxy, the concept of integrated galaxy, IMF, and in general on early stages of formation and resolved stellar population in clusters. And of course, she's also an expert on using Gaia data. She also wrote several papers on this aspect as well. So thank you, Teresa, for being with us. And Andrew Hopkins is a professor of astronomy at Macquarie University. I hope I pronounced it correctly. Andrew, and please, sorry if I didn't say it properly, in Sydney. And thanks for being with us today. The research of Andrew focused mainly on galaxy evolution and also the impact of star formation and environment on galaxy evolution, in fact. And of course, obviously the IMF is one of the main ingredients, on the basic ingredients. And I want to emphasize that, okay, Andrew has a very big production of relevant and remarkable work, but something I want to really recommend reading is the review that Andrew wrote in 2018 on measuring the initial mass function. Is a please to read. It's really a very nice review. So thank you, Andrew, actually, and it was a pleasure to read it. And so I recommend everyone to have a look at it. In fact, you might have noticed we have a small subset of interesting papers that we have put on our pages, on the duologue pages, where then you can use them for reading. Of course, we were discussing that 1 minute ago. If you put the word initial mass function on ADS, you end up with like something like 20,000 papers. So the literature is clearly immense, but this is but this review that Andrew wrote is really nice reading. At this point, I conclude by just giving basically an overview of the structure of today. I'm gonna be the moderator for today. So we will have the two talks at the beginning from Teresa and Andrew of 20 minutes each, and the talks are then followed by the dialogue part. Again, we do not intend to have really a debate flavor, but it's more a dialogue, which is done by Teresa and Andrew, and of course everyone is absolutely, and the scope is basically to dig into the open questions related to the science topic of today, which is the initial mass function. And of course, everyone is more than welcome. Actually, absolutely, we ask people to please, I see Hans Zinegger, I see Pavel, everyone is there. So thank you for being with us, Hans in particular, because exactly it's 5 AM in Chile. Thank you, Hans, for waking up so early. But we are doing this because, of course, it's not easy to find always the perfect time for we were discussing this 5 minutes ago. So thanks for being with us. But anyway, just to give you technical detail, the event is then will stay on YouTube, and then people can watch it later. So please make questions during this event. I'm going to monitor the chat, the live chat on YouTube, so people are absolutely welcome to write on the chat, and I will be happy to Hansi Pijama. This is funny. So and I will be monitoring the chat, and then we pass the question to our speakers. At the same time, if you do not have a Google account, you can still send your question using the dedicated email esoduo2020@eso.org, or you can go to our pages duo.eso.org, and there is a form on our webpage that you can use. You can post your question there, send it, and we will receive it immediately, and we are live checking our email, so we will also address those questions. As a final point, I would like to tell you that we created a pool. This is just to start the general note that I want to say is that, of course, this event is meant for professional astronomers, but everyone is welcome to send the question, of course. And in particular, we would like to ask our attendees, and I will post this during the event. We would like to make a pool among the attendees, and so the link to the pool is already available into the description of the event on YouTube, but I'm gonna now post it again on the chat. Basically, the question is very simple: is the initial mass function universal or not? So please, and then I will tell you the numbers at the end of this event, but we'll keep it open for a couple of days so that we can collect some statistics and see what people think about the IMF. With this, I think I'm gonna close, and I will ask. We'll stop sharing now. You're gonna see Teresa and Andrew. Please, just another final, sorry Teresa, just to make a final point, please remember that there is a 10-20 seconds delay basically between what we do on Zoom and what is seen later on YouTube. Teresa, please, now you can start the first talk. Okay, so.
Okay, can you see my slides?
Yes.
Okay, perfect. So hello everyone, thanks for joining, even though it might be extremely early in the morning for you. And I would like to start today's discussion with looking at the result star population and focusing a bit on the history and the current status. So let me start at when it all started. So we are in the 1954, 1955. That was basically the time when the understanding of star evolution and the fact that the stars die was basically in the air. And for example, globular clusters were being discussed from the point of view of missing massive stars. So that's where it all started. There was a particle physicist, Edwin Salpeter, located in Australia. So I think it's quite convenient that we are at the Australian timeline. And what he did is he basically defined something that is called, in his first paper, original mass function. And what this function actually does, it tells us the number of stars in a given mass bin that forms over some interval of time. So basically, the concept is pretty simple because the original mass function basically only tells us which stars are rare and which are common. But it's not as simple as it sounds, because what Edwin Salpeter did required a huge intellectual leap at that time. So by this counting of stars, realizing the fact that some stars evolve and die, he basically managed to connect at the time very new theory of quantum mechanics that he was expert in to cosmology, and he addressed the cosmic matter cycle and chemical enrichment for the first time by correcting for the evolved and stars that died. And it basically dates the start of the modern astronomy as we know it, because it allowed us to do simulation to understand how stars produce matter and new stars are born. Interesting to mention, I'm not sure exactly at what year the term of the initial mass function has been used for the first time. So the first reference I found is from Alan Sandage studying the stellar initial mass function of star clusters from 1957. And just about an hour ago, I received a reply to my email from John Scalo, and he also mentioned that the possible candidates to making this name initial is Jacek and Jacek on Vandenberg. So I don't know, you can comment on this in chat if you have more information. So now let's have a look in a bit more detail to what is required and what Salpeter and his accessors actually did in order to estimate the original or initial mass function in our neighborhood. So we are in a galaxy somewhere here, and there is a volume that we can observe up to certain completeness. And if we look into this volume, it's not simple. So it's a mixture of population. There is a disk, spiral arms, all built up during the complex star formation history, self-enrichment, chemical evolution, and of course these stars that we see around Sun now did not form here. So it's a pretty complex stuff that we are dealing with here. Nevertheless, it cannot stop us from counting stars and binning them based on their luminosity. Based on this, we can compute and measure, basically, that's the measured quantity, the present day luminosity function. So we know what bright stars are rare and which bright stars are quite common. Then there is actually very complex set of steps that needs to be taken into account. So we need to actually get to the stellar masses, but not just the stellar mass luminosity relation is needed, but we need to correct for an immense amount of biases. Note that, for example, the unresolved binaries is a very important issue here. And if we do all of this basically required 50 years of development over time. We are still not going to get the stellar initial mass function, but we just get the present day mass function. I don't have time to go into more details here, but note that there is a really nice feature hidden in all this machinery, and that is that by counting stars, we can actually look into the internal structure of stars, because the internal structure of stars is set by the star mass, as well as its luminosity on the main sequence. So this is actually quite beautiful aspect of this. And now the final step that was invented by Salpeter is to correct for the fact that stars don't live forever. And in the volume that we have nearby, we don't see the stars that were massive and died a long time ago. So if we correct for these, we obtain empirical inferred initial mass function. And now keep in mind all the biases I mentioned about the complexity of our neighborhood, and also realize that just because of these corrections, we don't see the stars that are not here anymore. IMF does not exist in nature. It's a health construct. It's something that we need to infer and create from the data in order to do measurements and calculations. Now, I think it's interesting to have a look at how the actual shape of this inferred field neighborhood initial mass function evolved with time. So on this plot, you can see masses of stars, and this is the stellar initial mass function. So this blue line is the first measured stellar initial mass function by Salpeter. Interesting to note, though, is the fact of the actual slope. So Salpeter at his time, he used the best data he had available. And at that time, people thought that the globular clusters, as well as Milky Way, are around 6 gigayears old. But Sinaker actually showed that if Salpeter would have used the correct value, that is 12 gigayears old, he would have to add more stars that died, and he would have obtained shallower slope, that is, he would add more massive stars. So now when we talk about the universality and the magical 2.35 number, I think that this makes you think a bit. Then there was a huge amount of work done by Miller and Scalo. They first time invented the multi-segment power law and the log normal fit to the initial mass function that drive the immense research in the theories reproducing this. Interestingly to note as well is that the slope of the high mass part derived by Scalo is actually different than Salpeter. It's steeper. So he inferred smaller amount of high mass stars required in the field. Now, the basically final word on this low mass part was done by Krupa in '93. Krupa, Taut, and Gilmore, they took into account unresolved binaries and discovered some features in the mass luminosity function that they overlooked. And basically, this part haven't changed since then. There also hasn't been that much development in the field start IMF that is still steeper. And this was also used by Krupa in '93, and it's still used in the literature. And now the high mass slope that is being used as the canonical IMF is not from the field, but is from Massey et al. '95. And they did not study the stellar field, but they actually did quite a large survey of spectroscopic investigation of nearby OB associations and star-forming regions in Milky Way and Large Magellanic Clouds. And their slopes that they derived are around -2.1 and -2.3. So they are also not a salpeter value, but it has been implemented in the literature that the slope of the salpeter is being basically consistent within the uncertainties with the data, and it's been referred to as the canonical IMF. This measured quantity can have different fits in the form of power laws or log normal. But I would dare to argue that I don't see much of the consensus here in the literature between the field and the actual star cluster counts at the moment. I think we have lots to expect from the Gaia mission. There have already been some papers, and I think what is the new feature that is now being allowed by the higher quality of the data is to simultaneous estimate of the IMF and star formation history. So I'm very much looking forward to the future Gaia releases in this aspect. Now, I mentioned that the high mass slope is constrained from the OB associations and star clusters. So maybe the situation for star clusters is going to be less complex than basically for the mixture of population that we see in the field. So we can have a look at really young star cluster and ask if we can see the IMF. But unfortunately, the cluster would say, oops, sorry, not yet, I'm still forming. So you cannot see the IMF yet. And then we would look just a little bit later, and then the cluster would say, sorry, I already ejected some stars and these two massive binaries merged, so no IMF here. So what I'm trying to say is that the star clusters, they have similar amount of biases as trying to investigate the star IMF in the field. We need to take into account the dynamical processes, mass segregation, and effects from binary stars that are very sensitive to initial conditions. There is a problem of field contamination, especially in the outer parts, that can bias our results. And of course, we should not forget about the star formation history that is not a delta function for star clusters. So the situation is very complex for star clusters as well from this point of view. However, despite all of this, it's not that bad. So there have been, I think, up to now, two large studies of Massey and Weiss that did a large statistical estimate of the IMF slope from various star clusters. And it works pretty well. So we can get a reasonably defined average despite the large uncertainties for the individual star clusters. But bear in mind that it was already pointed out by Scalo in 1986 that making an average over these samples only makes sense if the IMF is universal, because if IMF would vary, then it's really not clear what we are making the average of, and we could actually remove some variations by that. Now, so what has been done usually is to assume that the IMF is universal and then investigate if in some extreme environments we can see some departures from universality. And there is indeed a large amount of literature on this topic, pointing out that in the high densities and low metallicities, we can see overabundance of massive stars relative to the canonical IMF. That is basically what Massey found. On top of it, there is also low density environment that is sort of on the other side of extreme environment in this case. And there is evidence for a lack of massive stars relative to the canonical IMF. So what I think would be very interesting to do at the moment is to take these variations with the environment and actually have a look what variations of the IMF are consistent with these more or less homogeneous samples of the data. Could we actually find in these data some variations from the average? And please have a look at this paper. It was also suggested by Scalo, and they are basically, I think, the only study that I managed to find that is not using histograms, but is using kernel distribution estimates. I think it might be an interesting thing to consider. Now, we reviewed more or less what happened with the IMF field of the result star populations. So I would like to address the nature of the distribution function that IMF by definition is. Now, please bear with me, I will make a point, but instead of looking at the formation and evolution of stars, I would like you to think about how to study formation and evolution of dogs based on the measured mass distribution function. So as for stars, you can actually create a distribution function for dogs. So what is expected to be found is that you would have actually quite a small number of really massive dogs. Then there would be the most common dog, I guess 10 to 15 kilos. And then also there are really small dogs. You might even find an analogy to brown dwarfs if you consider hamsters or something. Now, you can also find the variations with environment at this mass distribution function, because you expect to find more small dogs in the cities, because people usually live in the apartments, so they don't buy big dogs. And on the other hand, you would actually expect a top heavy mass function of dogs that live in the villages. So what I'm trying to say with this is, it looks pretty much similar to the situation that we observe with stars. And now I would like to ask you what we actually can conclude about how dogs are formed, just based on this information at hand. So to put it from a bit different perspective, it's clear that if we have any distribution, measured quantity of mass function of dogs or stars, we can clearly mathematically randomly sample from the distribution and obtain statistically equivalent sample. But my question is, can we randomly sample individual systems, dogs to family, stars to clusters, and ignore the physical constraints? So my worry here is that if we would do it, we could actually get a too big a dog for a house, or an O-star that appears in the t-theory association and apologizing for blowing it all apart. So there is one view that we can have on the fact that IMF, as we constructed it by definition, is a distribution function. We can say that massive stars form stochastically with low probability, with living with the consequences of sometimes having too big a dog for a house. Or we can have a look at it differently. We can say that the physical conditions that are required for massive star formation are rare, but it's not random. So formation of massive star is physically determined. Of course, there is always going to be some scatter in the data, because binaries and n-binary interactions could sort of make it look more random than it actually was when the star was born. And now, there is not much about this in the literature, but I found this pretty nice paragraph in the John Scalo's 1998 paper, so please allow me to share it with you. Astronomers working on the IMF, like scientists in the other fields, have always been rather desperate to arrive at a definite result, as evidenced by the trend in recent years to reinstitute the salpeter IMF, despite the abundant evidence to the contrary in the literature reviewed here. It's 1998. Part of this urge, I think, is a result of a hope or faith that the complex and varied physical processes involved in star formation should somehow result in universal statistical properties. This belief is perhaps rooted in results from the velocity distribution found in kinetic theory and statistical mechanics, and the power spectrum found in incompressible turbulence. However, the IMF is by nature very different from these cases. And I hope that my example with dogs helped to emphasize this point a bit. Now, before I conclude, I would like to put this into a little bit more general context. So I think we are extremely fortunate to be living in 2020, because we've had Herschel, we have ALMA, and we can actually observe the embedded phases of star formation. We learned that molecular clouds are filament structured, And we can observe in all these bands that were not visible before. We also, from these phases, the initial formation of star formation, initial conditions of star formation are modified by star feedback, star dynamics, and star evolution, and reveal basically the naked products of star formation. And we can now take a huge advantage of Gaia in order to study these. And now the galaxies as such are created from these regions. So now today we have the unique opportunity to take the knowledge that we learned in these fields and basically build up the galactic star population and finally try to understand the complexity of the stellar neighborhood and possibly interpret what exactly is the IMF in the field that we can observe. And now I would like to summarize and give you some takeaways. So I would like you to remember that Salpeter's 1955 paper was a groundbreaking concept of the stellar initial mass function that basically demonstrated the usage of quantum mechanics in the sky and dated the start of the modern astronomy as we know it. I also would like you to remember that IMF does not exist in nature. It's our construct that we need to do models. I would also like to emphasize that it's one thing to reproduce the IMF from a theoretical concept. There is a huge, immense amount of literature on this, but this is not the same as using IMF and try to reproduce the properties of individual systems. Remember the two pick a dog for a house. And now there was a conference in 2005, the 50 years of the IMF. I think it was the last conference at which Salpeter was. And in his proceedings, he mentions there surely will be variations, but just what is still not clear. So I will dare to put there what we now think in 2020. I think significant variations are confined to extreme environments, and these are evident today. And now possible variations in our neighborhood, where the conditions are more uniform, remain to be explored. And I haven't been to that conference because it's too long time ago, but I would like you and myself as well to bring there and see what could possibly happen. So this is Hans Zinecker and this is a Salpeter, and I can only think what could happen. But I guess that Hans could say, "Look, Edwin, the non-Salpeter IMF trio," and they were watching the Scalo, Chabrier, and Krupa passing by. And I don't know exactly what Salpeter said at the time. I can only guess that it was something similar as written in his review. But what I would like to know, really, is what he would say if he could be here now. Thank you.
Great, Teresa, thank you very much. It was really, really excellent, very inspiring review and talk. Thank you very much. So I would like now to give the floor now to Andrew, please, for the second, and I will leave the, and then you can start the discussion later. So please, Andrew, go ahead.
Thanks very much, Giacomo. Teresa, I think you need to stop sharing your screen before I can show mine. Thank you. Well, thank you again very much, Giacomo and the rest of the organisers of this event for giving me the opportunity to participate. It's a fantastic event. I'm very excited about being able to be part of it. And thank you very much for being generous enough with the time shift to make it a little more convenient for participation from Australia. And I want to say a very special thanks to Teresa. She's done the heavy lifting in the conversation already with the presentation that she's just given, covering a substantial amount of critical pieces of the very, very complex picture that we're talking about today. And I hope that I'll be able to add a little to that, or although I suspect that it won't do justice to the wide range of aspects of this very complex topic. So I'm going to focus on measuring the IMF. Teresa has given a fantastic introduction to what the IMF is and a lot of the history and the context, with a focus predominantly on the stellar IMF. So I'm not going to talk about that at all. Teresa has done an amazing job at covering all of that in incredible detail. I will talk a little bit about approaches that have been taken over the last few decades in exploring different approaches to measuring the IMF in galaxies, resolved galaxy populations, but also unresolved galaxy measurements. I'll introduce the concept of a cosmic IMF, which has come about probably in the last 15 or so years as essentially a self-consistency requirement between various different cosmic censuses of galaxy populations. There are other approaches to measuring the IMF as well. Chemical abundance measurements are one of those. All of these different approaches tell us something different about the underlying physical processes going on in stars and in the galaxies that they form. I won't talk about chemical abundance measurements today. The approaches of chemical abundance measurements to the IMF obviously require resolved stellar populations. And this really limits them, at the moment at least, to the Milky Way predominantly and nearby galaxies where stars can be resolved. I'm going to make a couple of brief points before I really get underway. Teresa touched on this as well just at the end of her presentation, but I'm going to be talking about the IMF as we measure it, or rather, as Teresa emphasised, as we infer it from other measurements. Using various observational approaches. There is a difference between the IMF that we measure like that and whether it happens to be a universal quantity versus the idea of whether there is a universal physical process that produces an IMF. And this is an important distinction and one that often gets conflated in discussions in the literature because a universal IMF may be a consequence of an underlying universal physical process, but the reverse doesn't necessarily follow. You can have a universal physical process for star formation that doesn't necessarily lead to a universal distribution of stellar masses. I've given a couple of references there, Naray and DeVay 2012 and Phil Hopkins in 2013. I think that there are a number of more recent references that cover that same, or illustrate that same point. And so the last thing I'm going to say on this is that there is an important open question that I'm not going to talk about today around whether the underlying physical processes that drive star formation might be a universal concept, or in fact whether the physics itself might differ at different epochs and in different environments. Second quick point that I'd like to make before getting going is a little bit of a rant. The whole field of the stellar initial mass function is an incredibly complex one with many physical and observational subtleties, and getting on top of all of those is challenging enough in their own rights. Unfortunately, as astronomers, we don't make our lives easy. Over the entire history of this field, there have developed a plethora of different conventions, terminology, language, all used to describe the same things, but doing it in a way that just adds a layer of unnecessary ambiguity. So even at the most basic, this might be whether you choose to include the negative sign in the exponent in the equation of the IMF form or in the parameter itself. And so there is an inconsistency throughout the literature, and indeed even within some individual papers about the choice of sign convention. Simple use of different symbols, different pronumerals for the same quantities. X or gamma are commonly used instead of alpha, referring to the slope of the power law IMF. And another example is using the same symbol for different things between different authors, and alpha shows up in this context a number of different ways, and I'll come back to that later. One of my real frustrations is whether or not the mass limits of assumed IMFs are mentioned or described in sufficient detail in publications, that you as a reader are able to actually understand what initial mass function parameterization was actually used. There's a very big difference between whether your upper mass limit is 100 solar masses or 120 solar masses, or if you have a change of slope at 1 solar mass towards the fainter mass end versus none, and so on. Related to that, ambiguous uses of very common terms like the saltpeter IMF, or a universal or typical or canonical IMF, without describing what it is that you actually mean by that. The phrase the saltpeter IMF has been used to mean vastly different things by different authors. Different phrases for describing the shape of the function that you're using, ambiguous use of words like flat, steep, upturn, downturn, turnover. And when you start to explore the variations or potential variations in the IMF, an entire language is developed completely organically. And I've given a few indicative phrases there, but they're often poorly defined. And so this really is a plea for consistency in usage, both of terminology and of language in descriptions of this very, very complex beast that we're trying to understand. Do have a look at the review article that I wrote. I have a much more well-argued, well-justified set of motivations to support this plea, which I'll point out has been reiterated by authors in this field going back at least 2 decades and probably even longer. The third quick point that I'll make before jumping into some of the details is introducing some new technology, some new terminology. Because of the different approaches that people have been taking, especially in the last decade or so, towards getting a handle on the IMF, it really has started to throw a level of confusion into the field. And as Teresa very eloquently pointed out, if you're measuring a star cluster and trying to understand the initial mass function from that, you're going to get something potentially quite different to what you end up with if you are looking at a galaxy as a whole. And if you then throw in the concept of cosmic census constraints, you're now looking at entire populations of galaxies. And what you are measuring in each of those different cases could well be quite a different quantity. That's absolutely true if the IMF is not universal. And so I'll come back to this again towards the end. So now let's look quickly at some of the work that's happened over the last few decades. And there's been an absolutely vast amount. I think Giacomo mentioned there are more than 20,000 papers on ADS that have the phrase initial mass function in their abstract. There's absolutely no way any individual can do justice to the wealth of papers that have explored this from a variety of different observational and theoretical aspects. And so this really is only a flavour. And I have to apologise that it's not possible to be more complete. I characterise two different approaches here for looking at the shape of the initial mass function in star-forming galaxies. The Kennicott method, which Kennicott first published in, I think, about 1983, looks at the equivalent width of the H-alpha line as a function of an optical colour index. The diagrams shown here come from work by Madhusha Gunawardena from 2011. What she shows are three representative tracks, each of which corresponds to an assumed initial mass function slope. The central initial mass function slope, the central line corresponds to an initial mass function slope of minus 2.35, the standard saltpeter slope. The slope above, the line above that is a slightly flatter high mass IMF slope, and the line at the bottom is a slightly steeper one. When you take a large sample of galaxies, and she's investigated 3 independent volume limited samples here, each of which have many tens of thousands of galaxies in them, what she finds is that as you increase the star formation rate of a galaxy, you tend to find flatter high mass IMF slopes. The high mass slope index alpha goes from minus 2.35 up to about minus 2.15. So it's not a big change, but it's a measurable change. And the sense is that as you increase the star formation rate of a galaxy, you tend to find a flatter high mass IMF slope, or a relative excess of high mass stars. The Buat method looks at the ratio between the H-alpha and the UV flux from a galaxy. The H-alpha emission is sensitive to a higher mass subset of stars than the UV, which extends down to about 5 solar masses compared to a lower limit of about 10 solar masses for the H-alpha. And so you might expect that as a star formation event occurs, the slightly longer lived UV emitters start to predominate as the H-alpha emitters fade away. So using this kind of metric, you can probe, it turns out quite well, the properties of low mass or low star formation rate galaxies. And what's been found using this approach is that the lower the star formation rate of a galaxy, the lower the abundance of the high mass stellar populations, or a relative underdensity of the high mass stars. So it goes in the same sense as the results from the high star formation rate population. The lower the star formation rate, the steeper the IMF slope, the higher the star formation rate, the flatter the IMF slope for the high mass end of the stellar population. Moving to passive galaxies, by which I here mean galaxies that are not active star formers, or at least have very modest levels of star formation rate. These are typically early type galaxies in the studies that I'm illustrating here. And I am not making any comment about whether or not AGNs are present. Passive here is in the sense of a lack of star formation. So a variety of different approaches have been used to explore the IMF slopes for these systems. This one from 2012 by Michele Capillari uses kinematic methods to estimate the mass to light ratio of the stars in this sample of galaxies. And they're able to compare those measured mass to light ratios with the mass to light ratio that you might infer if the IMF had a saltpeter slope over the full mass range from 0.1 solar masses up to 100 solar masses. The diagram shows for a variety of different assumed dark matter halo profiles. The result doesn't change regardless of the assumptions about the dark matter profile, that as you go to the higher mass to light ratio systems, which generally speaking tend to be the higher mass galaxies, you find that their mass to light ratios are substantially in excess of what a saltpeter IMF slope would tell you. This has been interpreted to mean that there's an overabundance of low mass stars in these systems. using a completely different diagnostic, the dwarf to giant ratio method, which relies on particular spectral absorption features that are sensitive to the ratio of dwarf to giant stars. There's actually been quite a substantial amount of work using this technique over the last decade now, and the results are all very strongly consistent in the sense that as you go to higher velocity dispersion systems, the expectation or the measurements are suggesting that there is a relative excess of low mass stars, so an overabundance compared to the saltpeter slope of low mass stars. So we're now looking at the low mass end of the stellar initial mass function in these systems. Another approach to mass to light ratio constraint is given here. This work uses gravitational lensing to get estimates of the mass to light ratio in galaxies. The alpha that's indicated on this diagram is not the initial mass function slope, but it's rather the ratio of those mass to light ratios, the same as in the work by Capillari 2 slides ago. So beware of inconsistent terminology usage. But again, the result here shows that for galaxies with increasing velocity dispersions, you can see an excess of mass, an excess of compared to the mass to light ratio you would expect from a saltpeter IMF, which again is interpreted as an excess of low mass stars in these systems. Moving on to cosmic census measurements. So the issue here is that if you take the total luminosity function for galaxies at any given redshift and integrate that up after converting it to a star formation rate, you can measure the star formation rate density of the universe. You can look at how that evolves over the history of the universe, and you can integrate it up over the history of the universe to infer what the growth of stellar mass in the universe would look like. So what's shown here from 2 papers by Steve Wilkins in 2008 is actually the inconsistent result when you compare the measured star formation history of the universe on the left with the star formation, the stellar mass density of the universe that you measure independently on the right. And the inconsistency is in the sense that if you are to invoke evolution of the IMF as an explanation for that, that you would need the IMF to evolve to have flatter high mass slopes at higher redshifts in order to resolve that discrepancy. More recent work has tended to dismiss that degree of inconsistency. In particular, a very well referenced, very well cited review by Maddow and Dickinson in 2014 attempts to explain that away. They've assumed a saltpeter IMF over the full mass range, 0.1 to 100 solar masses, neglecting the change of slope below a solar mass or so for convenience, and that's fine. And they claim that the slight excess when they compare their fit to the star formation history and integrate that up to get a stellar mass density history, the slight excess that they identify there of 0.2 dex is reduced to 0.1 dex if you take what they call more typical Milky Way IMFs into account. That 0.1 dex is still there, however, and I've made the point previously and in different venues that there are missing data. They've been very selective in the choice of data for very good reasons in their compilation, but the data that they exclude happens to be the data which shows higher star formation rates at the mid-redshift range, redshifts 1 to 2, 1 to 3, and that there are also more recent estimates of the high redshift star formation history that may be rather higher than those that have been assumed here, and that will have an impact on the functional fit and consequently the integrated value. And so I think that the tension there has not really gone away completely. This appears in a slightly different context in a more recent analysis by Simon Driver and colleagues, looking at over 500,000 galaxies from 3 very high-profile surveys. Their results are shown with the black data points in these diagrams and the grey uncertainty regions around them. And when you compare the integral of their star formation history, the star formation history shown on the left, and the integral of the stellar mass density on the right, you can see that there now actually appears to be a slight tendency for an underestimate of the stellar mass density at the very low mass end from this compilation of data. So I do think that there is still room for exploration of this. And I find it intriguing that a very recent analysis looking at the integrated galaxy IMF model applied by Kraslinska just earlier this year show that that particular model is efficient at reducing the star formation rate density at higher redshift, which is, again, in the sense that would be needed to resolve this discrepancy. So that's a lot of information very quickly about a lot of approaches in very, very different contexts. So let's just take stock of where we're up to after all of that. As you saw from Teresa, the stellar IMF, I'm now using the SIMF, GIMF, CIMF terminology that I introduced a little while ago. The SIMF does seem to show some degree of variation within different star-forming regions and between different galaxies. The GIMF, the galaxy IMF, as measured by the Kennicutt method, the Buat method, and compared against the various methods used for the passive galaxy population, seems to show dramatically different results in the sense that high star formation rate systems seem to have flatter or more top-heavy IMFs compared to high mass passive galaxies having bottom-heavy or an excess of low mass stars in their IMFs. But these have not been tested self-consistently, and they haven't been any analyses that so far have been able to look at both galaxy populations self-consistently. And I'm going to come back to that in a minute. There are some hints of evolution in the CIMF, the cosmic IMF, and I think that those haven't gone away just yet. So taken together, I think all of these really point to a change of philosophy as astronomers, as astrophysicists. We need to recast the question about is the IMF universal to a much more well-posed concept. How much does the SIMF, the GIMF, CIMF vary, rather than is it varying at all? This is a necessary step forward. The challenge in doing this, of course, is making sure that the measurements can keep up with what we would like to try to infer from them. And I'm going to come back to that again in a minute as well. It is important at this point, I think, just to emphasize that when you are starting to think about how you encapsulate the concept of a varying IMF, there are now a wide variety of completely open sets of parameter space to explore. The approach taken by the Krupa IMF, Integrated Galaxy IMF model, I think is very instructive in this sense. I expect that there will be a plethora of various models starting to show up on the scene to try to link the 3 observed types of IMF. So in order to help with all of that, one of the things that I've tried to do is make a suggestion for thinking about looking at different diagnostic diagrams that can help in giving a handle on what it is that we're measuring, and using them explicitly to differentiate between the different IMF regimes. So this is a diagram that shows the high mass slope of the IMF as a function of redshift for the cosmic IMF. And what you see here in the dashed line is the salpeter slope, minus 2.35. The dot dash line is a slightly flatter slope of minus 2.15. And this is what Steve Wilkins found in his work back in 2008, was the best guess for fitting the low redshift end of the star formation history of the universe. And it turns out quite a modest level of evolution that he subsequently proposed, as you can see in the solid lines with the shaded regions of uncertainty around them, in order to eliminate that discrepancy between the star formation history and the stellar mass density history. So if there is evolution in the CIMF at all, it doesn't necessarily need to be a lot to resolve the observational tensions. Turning to the GIMF, the galaxy-wide IMF, this is two different diagnostics, one showing the high mass slope of the IMF as a function of redshift, the other showing it as a function of the surface density of H alpha. In terms of redshift, you can see that there's quite a broad range in the inferred IMF slopes for star-forming galaxies for the low star formation population from Muro 2009, the slightly higher star formation population at low to modest redshifts from Gunawardena 2011, and at higher redshifts from a more recent analysis looking at the same diagnostic, but in this higher redshift population. Each of these analyses published trends of their inferred IMF slope as a function of various galaxy parameters, which I've recast here in terms of the H alpha surface density. And it's intriguing to see that there is some hints of similarity here, but obviously not everything is in complete agreement, and there are very, very large uncertainties. I think approaches like this that people might explore to start narrowing these ranges of uncertainty down are potentially quite promising. Things get quite striking when we look at the passive galaxy population on one of these diagrams. I'm showing now the low mass end of the IMF and the slope that's associated with the Krupa or Chabrier versions of the Milky Way IMF. So having that standard kind of turnover shape to it. And where I've shaded the region that I've labeled Milky Way at the top of the diagram is a very rough estimate of the formation period of those stars in the Milky Way. The high mass passive galaxies that have been explored with the kinematic and the mass to light ratio and the dwarf to giant ratio stellar indicators show a dramatically different result in this diagnostic, and there's really quite a striking difference there. I think there is a lot of opportunity to try and explore where those differences might start to come from. So, wrapping up, the puzzle of the stellar mass function is real. It's a complex challenge, and as we have said, a substantial and growing amount of research in the past decade. I was just on ADS earlier trying to look at the annual deluge of papers, and it's something of the order of 500 papers a year on the IMF that keep coming out. So it's not a negligible field. It touches on effectively every aspect of astrophysics, as Giacomo mentioned in the introduction. There's a lot of work that's been happening, and we now have a vast array of new observational tools, as well as theoretical tools. But there are a wealth of apparent inconsistencies that have resulted as a consequence. In order to address those, we need the conversation to move on from the question, is the IMF universal? The question needs to change to how much does the IMF vary in each of its different contexts, and for observations to be able to rigorously quantify random and systematic uncertainties to help in constraining this. I think there's a bright future for the field though, there's a huge scope for the kinds of population synthesis and SED modeling tools that are critical, especially in the measurements of the galaxy and the cosmic IMF observations, to be refined and extended in order to self-consistently test and compare different IMF metrics and potentially identify new ways of getting observational handles on this very tantalizing quantity. And it's important to explore models such as the IG-IMF to explain the observed differences between the measured IMFs. But in order for that to be an effective approach, the observations really need to be well defined. And I come back to my pedantic approach for a plea to authors to use well defined conventions and definitions in their work. So, and this is the last slide. Is it universal or not? I'd like to leave you with this point, which reiterates one that Teresa already made. If the IMF is assumed to be universal, it can never be demonstrated that it is. So let's set aside for the moment that the question is poorly posed. Assuming the IMF is universal ironically rules out the capability to identify that it is, only that it's not, if observations unambiguously falsify the assumption that you've started with. One of the other challenges is that if you have an assumption that the IMF is universal, or worse, a bias or a preconception that it is, what tends to happen is that any discrepancies with observations tend to be dismissed in one way or another. And the conclusion is simply that your observations are consistent with the universal IMF that you pre-assumed. This doesn't give any new insight at all into the problem. On the other hand, if there are IMF variations, they can only be measured with tools and techniques that have been developed with those in mind and implemented self-consistently. It's that self-consistency which is really challenging and still very critical. This has the added advantage that if the IMF doesn't vary, those same tools can be used to place ever tighter constraints with quantitative measurements describing the degree to which the IMF is or is not universal. So what I would like to encourage everyone to think about and to move towards is the default assumption that the IMF may vary, because that really is, as far as I can tell, the only way that we're actually going to start to make real progress in this very, very complex field. Thank you all very much.
Wow, thank you, Andrew. So for the very nice talk. And first of all, I would like to pass, I don't know if you're looking at the chat, but you would like to pass the congratulations to both again for, and I'm going to applause. I'm going to be the only physical, then you will be physically here now, but because there is a lot of, you know, positive feedback, and thanks both for the great talks, really. So we can now, so first I would like to say the first result. I don't know if I can say there's now ready for the pool. So I would like to remind people you can still vote. I'm going to post now the I'm going to post again the form, but basically we have 60 responses so far, and we have 10% of yes. So 10% of yes, the IMF is universal, and 90% no. But of course, but this, I mean, you gave some very important point. You made a very important point, I think, both of you. So I would like to start maybe by asking yourself if you have questions to give you the priority. Basically, if you have questions that you want to make one to each other, just to start the dialogue. And then there are a number of a few questions that that people have posted, so I will make them later. But if you want, Teresa, and take the word.
So can I start? Andrew, is it okay with you? Because I have a question. So I very much like the idea of distinguishing the stellar IMF, galaxy-wide IMF, and the cosmic IMF. And one can already see this is appearing in the papers and literature. For example, Romano 2020 is using galaxy-wide IMF, which I think is great. But my question is, do you think we would also use maybe some in-between term, maybe a composite IMF? Because sometimes we cannot observe the full galaxy. And for example, with the field IMF, we just observe some region around us.
Yes, I think that is inevitable. I think that in choosing those terms, I was really trying to get people to start thinking a little bit more subtly about what it is that we're measuring or attempting to infer, and the different range of physical scales over which we're doing it. So yes, absolutely. I think what I would like people to be able to do is to start to do the kind of analyses that have been used for galaxies, where people try to compare IMF slopes as a function of H-alpha surface density, for argument's sake, in different contexts. Obviously, when you start getting to extreme small scales, something like an H-alpha surface density no longer makes sense. Because if you have a single star-forming region, for argument's sake, the total volume and the area are in a completely different regime to a galaxy, and the empty space between star-forming regions in a galaxy that you count when you're looking at the surface density aren't there. So I think trying to extract more relevant physical parameters that are linked to the underlying star formation processes and compare the IMF properties that get inferred as a function of those parameters is really where the field needs to start moving, to be able to link the inferred IMF shapes to the astrophysics in a way that starts to make the whole problem a bit more concrete.
So would it also take care of the problem of the time? Because sometimes we observe the sort of, if we look at the H-alpha, right, is the recent star formation. And if we infer IMF from it, we get the population of stars that is forming now. But if we, for example, look at the early type galaxies, it's the IMF integrated over the whole formation history. So how to tackle this?
Yes, absolutely. The time dimension is the other confounding factor. And I do discuss both of these issues in the review article. So I would encourage people to take a look at it. One of the issues with the time dimension is that you can, as you were describing yourself actually, try to average out the properties of the IMF if you sample enough different representative objects. So you're catching them a sufficiently large number of their different evolutionary states, that what you end up inferring corresponds to the underlying property that you're trying to measure. And as you rightly pointed out, that necessarily requires the IMF to be the same in each of those locations, because if it's not, then what you get is some very complex picture that you can't untangle, you can't disentangle the underlying variations. So yes, I think that there is a challenge in many senses in trying to self-consistently interject the variations or the possible different astrophysical processes that might drive a different IMF shape in different regions at different times. And so that makes the problem very complex, but it doesn't mean that we should stop trying to understand it. I have to say, I was very impressed with your canine analogy. I thought that was a very, very clever way of illustrating the point about the role of massive stars in the challenge of understanding how an IMF can be represented when you have pool of gas that you're then trying to form a set of stars from. It's a quite a nuanced problem in a lot of ways. So I like that a lot. Thank you.
Yeah, indeed. So, so Andrew, do you want to do a questions that you would like to or?
No, I'm happy to open the floor up to the viewers.
Okay, so so there is a question for you, Andrew, in fact. So if you can give your feeling about the fact that the kinematics and that you get, for example, Atlas 3D and versus weak absorption lines, dwarf and giants method applied to early type galaxy give similar trend but not consistent values. What's your opinion on that?
This goes to one of the things that we were talking about earlier, quite a specific question about some of the technicalities of these analyses. And there are many papers that have been published on this over the last 5 or 8 years, I think. So I think that it's going to be a challenge to give a comprehensive answer. My sense from the conference in Leiden a few years ago now was that those different approaches give qualitatively similar results, the sense of progressively more bottom-heavy IMF as you go to higher mass galaxies. But when you look at them quantitatively, you see some differences. And I think the answer to that is probably to do with the specifics of the samples that are being selected. And that it's not necessarily just the galaxy mass or the galaxy velocity dispersion, which is the underlying free parameter. Beyond that, I would have to defer to the experts, and I'm sure that there are many of them online who might be able to provide a more specific response to that particular comment.
Okay. Okay. So we have another question here coming. Question: can we? I'm going to read it. Okay, as it is written. Can we inform the slope of the IMF from star formation simulation for given environment? For a given environment, or there are too many uncertainties, and if so, it is consistent with observed slopes. So I guess if you can, I guess the idea is to go a way around. You do simulations, and you yeah, please, and then you see what happens and how it compares with observations, basically.
Yes, and people do very much. The approach from simulations has been used for many years to try to get a handle on the resulting IMF slopes and shapes. The challenge there is knowing exactly the input physics to use, and different simulations focus in different ways on different aspects of the physics, whether it be the turbulence or the environment or the magnetic field structures or whatever else it might be that goes into those recipes. And of course, depending on what those assumptions are, the results change potentially quite significantly. One of the things that the simulations can help in telling us is how things change when those different input parameters are varied. And I think that there has been quite a lot learned over the last few years on that front. But in part due to the very conflicting nature of the observational constraints that they're trying to compare with, I don't think that there has yet been a concrete conclusion coming from the simulations around the dominant physical processes. Do you want to add to that, Teresa?
Yes, yeah, indeed.
Can I please?
Yeah, please, Teresa. Yes.
So what I would like to say that it's actually not that difficult to reproduce the power law or a log normal or polynomial slope resulting from the random processes. It's something that is called Zipf's law, and it's actually demonstrated everywhere in the nature. So if you open a random book, the distribution of the length of the letters is going to be a power law with a given slope. Or the monkeys writing on a typewriter with different assumptions will result in the log normal or a power law. So it's actually well known that if you mix together the bunch of complex processes, it will result in something sort of similar to the IMF. And this is basically the statistical approach that was started the first paper by Hans Sinecker in 1884. And this is valuable up until now, when there was the recent paper just a few days ago on an archive. And I would like to add to what you said, that it's important to have a look how the theory varies. So in the Essex 2020, there is actually a last paragraph that is discussing what variations can be accommodated within the theory. And I think that this is actually very important because it can distinguish between the abilities of different theories based on the ingredients that are put in, the variations that can be reproduced in that concept.
Yeah.
And I'll come back to emphasising the need for observers to place very well-defined uncertainties on the measurements, because that's absolutely crucial for any of the underlying theories or the simulations when they're trying to compare with reality.
Yeah. Okay. So so a question then at this point, maybe for Teresa, and then also, so where is which is the best place, or if there is one, or the ideal place where to measure, to try to infer, okay, a law, an initial mass function, or even though, as you mentioned, it's just it doesn't exist, okay, which I understand point, but because I was thinking, on one side we look at the solar neighbors, okay, we see, but the solar neighbor, the complexity is such, because you have so distribution of metallicity, and so it means already that the star formation history is complicated. Then you have binaries, then you have, while if I was thinking, this is very naive, but I was thinking, if you look at a cluster, even a globular cluster, okay, which star formation history we found that is really not as easy as we thought, but the Pleiades, I will say, okay, if you look at the Pleiades, okay, it's, I mean, I think you can easily, I mean, it's more the control, I mean, say that you have on the physics, it's easier in a sense. What do you think about that?
Well, you would think so. But if you look at individual clusters, it's actually amazing. Open any paper. Now, this is not that much done, but in the past, people were actually looking at the individual clusters. And even if you look at the Weiss 2015 paper or the Massey paper, the individual cluster-to-cluster variations are huge. It's around 0.4 dex in the slope.
Variation of what you mentioned?
So you look at the star cluster, and you try to measure its IMF. So in the case of Massey, for example, he was looking at the high mass slope. And then he has a table. So what he did, he counted the massive stars based on the masses, he made a histogram, and then he made a fit and estimated the Poissonian scatter, basically given the scatter in the histogram. And then you estimate some mean value that has, you know, it's different than the salpeter, and then the scatter is around 0.x. That is huge. It's basically, you cannot tell if it's universal, if it's flatter or steeper. The scatter is really huge. Then what has been done with these values was to average them, which of course reduces the scatter if the variations are not huge. But the problem with star clusters is that even if you imagine that the IMF would be exactly sampled, so there would be no intrinsic variation, so you would know exactly what star, imagine idealistic model. So you put into your simulation exactly what star you want to have, and then you let it evolve. It's complicated because binary stars merge, get ejected. The cluster evaporates stars.
Yeah.
It gets disrupted in the tidal field. And this all depends hugely on the initial conditions. So it's not as easy as it sounds.
No, I'm not saying it's easy. I'm just saying I completely agree. It's not easy. But what I'm saying is that maybe the all these ingredients that you're mentioning, I mean, I naively, I think if you look at the field, it's much more complicated because you have very little control of the past history of the galaxy itself, even instead of looking at a cluster, which is, okay, you put it in a potential well, you make it evolve, you have more or less a control of n-body. I mean, because you have to, again, you have to distinguish between the present day mass function, so you measure what you measure today and what it was at the beginning. And that's the challenge, right?
Yes.
So, okay. But I don't know, I thought, while reading also the review, and by reading, I thought, well, clusters are not that bad in the end.
When you mentioned Pleiades, I think there is still an unresolved issue with the low mass star content. I don't remember by heart the reference at the moment, but if there is someone aware of this issue, please put it into the chat. And I think also Scalo mentioned it in the email I got just this morning, so I can find it later. But it's really difficult, and I think we sort of stopped investigating these things in a detail, because when you assume the IMF is universal and it's randomly sampled, why would you bother with explaining individual clusters if you can blame everything on the random processes, right?
Yeah, indeed.
Just on the point of the globular clusters, there's a very interesting result which I have in the review about the inferred IMF slopes for young globulars versus old globulars, which in an intriguing way seems to parallel the results for star-forming galaxies versus passive galaxies in terms of their inferred, well, in fact, in terms of their inferred total mass in stars, not necessarily the shape of the IMF, but the total mass that you associate with those two different populations. I think that's a very tantalizing result, and there's more exploration.
Yeah, and maybe just to add one more thing. Maybe it looked a little bit like it's too complicated and we cannot do anything, but actually the constraints are pretty large. So it's not like we would have complete freedom, but actually if the IMF is varied too much, we get into trouble and complete disagreement with observations pretty fast. So it's not completely unconstrained, but just to get the exact value, pinpoint exactly what it was, is difficult.
And this, I think, again, is where having a set of diagnostic tools and the very sketchy figures that I showed are just a suggestion of a place to start on this. I think if people start thinking about using diagnostic diagrams like that, it's going to be an incredibly helpful way of visualizing the bits of parameter space that are being constrained and the degree of uncertainties that go along with the different sets of measurements.
Okay. I have another question that was in the chat, actually. I think it was for you, Andrew. So I'm going to read it. May I ask why there would be underestimated star formation rate through low frequency radio observations?
Through low frequency radio observations.
Yeah.
Okay, so let me take a stab at that. Radio observations are kind of a latecomer to the party when you think about measuring star formation rates in galaxies. They've been used probably for over 20 years or so now. There was a review article by Jim Condon in 1992, I think it was, that it described the use of radioluminosities as star formation rate indicators. The challenge with radio data is that in order to probe the star-forming population, you have to get very, very sensitive measurements. And it's really only been in the last 10 years or so, the last 20 years perhaps, that the star-forming population has been able to be sampled in sufficiently large numbers to start looking at the star formation history from the radio measurements. And that's so far really only been able to push out to redshifts of 1 or so. There was a recent, relatively recent article, I think the first author was Novak, that looked at the very high redshift population from radio data. And their star formation rate densities were measured to be substantially higher than the compilation from McGowan Dickinson. They're not the only outlier in that sense, but it's intriguing that a result from the radio is consistent with a result from other recent measurements from Herschel data in the infrared, and also from suggestions coming from gamma ray burst rates at the very highest redshift end as well. So there is, I think, at redshifts above 4, 5, 6, still some unresolved tension in the star formation rate density of the universe at those redshifts. I do think that there's scope for exploring that further. I've suggested in the past that there's need for another review of the star formation history to try and put together some kind of a gold standard sample, reference sample, that really looks at all of these issues. That's a vast, vast piece of work in its own right as well. And so I don't see anyone putting up their hand too quickly to do that, but I think having that would be an incredibly valuable resource for the community, given the constraint that the star formation history places on so many different ways that we look at galaxy evolution, not just the IMF, but it's one of the canonical reference points for simulations and models to reproduce, among many others. I'm not familiar off the top of my head with work that looks at low frequency radio data, although perhaps by low frequency they just mean radio data in general in the context of measuring star formation rates.
Okay, on this line, actually, there is another comment that I wanted to read. So coming from radio background, what is your opinion on using molecular line transition ratio observation in constrained IMF variations? It's mentioned, for example, 13CO versus C18O. But this, yeah. So what is the future of these? And it can be a good tool to move comparison galactic versus galactic linear extragalactic sources.
I think the more tools that we have to get a handle on the properties of the IMF, the better. This is one that I'm not very familiar with myself at all. I saw Teresa nodding, maybe she knows a little bit more about it than I do. Do you want to comment, Teresa?
So I don't know the exact details, but I would like to point out that I think this is extremely promising. So there was a Zhang et al. 2018 Nature paper that used exactly these ratios because, so I don't know the details, but the trick is that that one can get a handle on the IMF because the ratio depends on the proportion of massive to low mass stars, because not all the elements are produced equally by different stars. I'm quite sure someone can summarize this way better, but it's a Zhang et al. 2018, and the chemistry was done in the previous paper, Romano 2017. So I think it's a great new method that is very promising, and they use the ALMA measurements too.
Yeah.
Yeah, I think, as you said before, Teresa, ALMA is a fantastic tool, and I'm really looking forward to seeing more use of it for approaches like this. I said before, the extensions to population synthesis tools, I think, is one area where there's a huge scope for developments, and they will make a big difference in our ability to understand the way that we measure or infer the IMF from, especially in the case of unresolved galaxy populations. And so I think ALMA will come into that context as well. But at the moment, the approach to population synthesis in galaxies is very optically oriented. It's only been relatively recently that it's been pushed into even the near infrared. And so really extending that very much into the full panchromatic spectrum in a way that other SED modelling tools have done for looking at photometric galaxy properties and doing photometric redshifts and stellar mass and star formation rate estimates. I think that population synthesis can really be pushed much more broadly than it currently is. So extending it to the radio, extending it to the millimetre, and using those additional observational constraints has a huge potential.
Yeah. So there are a few more. I mean, we are running a bit out of time. It's 1 hour and a half. This is typically the length we would like to keep. But let me maybe. So I'm trying to follow the chat. So there is let's say I can summarize. There is a long questions related to basically our understanding of it is okay. I can read it to you, Teresa, just because it was back on the interpreting and understanding IMF in clusters. The point is, it is difficult as we don't understand the theory behind cluster evolution in its environment variation yet. Okay, so or it is an issue of uncovering the evolution history from observational traces. That is, using present-day observation to infer the IMF. I guess both, but which is more dominant? Open question.
Okay, so I'm not sure if now I understand. So the question is whether it's difficult to infer IMF or the initial conditions, which is more difficult?
So which is more difficult so is this the issue of uncovering the evolution history from observational traces? Okay, so yeah, I'm trying to read it again. So sorry, Teresa. So theory behind, so cluster evolution environmental on one side, and yeah, so from one side is the theoretical part, so as you said, so, and on the other side is our capabilities of using the present day observation to infer the IMF.
Yeah, so they are unfortunately related. So yeah. If one cannot infer how the cluster looked at the beginning and how it formed, it's difficult to infer how its initial mass function looked like. Maybe I forgot to mention, but I also showed it in my slides. It's not always necessary to infer the initial mass function. One can just try to also observe the trends with dynamical evolution and ages of the clusters, as was done Demaci and collaborators in 2010. So it's not always that important to infer the initial mass function in order to understand the dynamical effects. But the problem, well, let me wrap it like this. We have now the more and more observations that allow us to observe almost all of the phases of cluster formation. But it's still pretty open question whether, for example, one idea could be that the cluster forms at the intersection of two inflowick filaments because it creates good physical condition, enough pressure. There is also cloud-cloud collision scenarios. So these are open questions, and it's very difficult to tackle these theoretically because majority of the simulations are right now the pure n-body, which is extremely good tool, but then you start already at not exactly the initial phases. So this tool is extremely valuable, but if one wants to actually understand how exactly the cluster formed, you would need to combine it with hydrodynamics, which is pretty much impossible at the moment because you need to capture the timescales of the n-body dynamics that are really small, while still being able to simulate it in the hydrodynamical simulation and resolve the stars. So that's the biggest theoretical obstacle that we are facing at the moment.
Yes. Yeah. Okay.
I don't know if it's here or...
Yes. So there is a discussion going on about the impact of binaries actually in information on massive stars, which is another big topic. That we, but since we have, I mean, it's a pity because that's the point of IMF. When you talk about IMF, you basically touch upon, I mean, formation of massive stars, impact of binaries, metallicity. I mean, how metallicity changes the star formation and the efficiency of forming stars, basically, and this is all a bunch of.
Can I just, is it being discussed whether IMF and binaries are independent or not? Because yeah. I think that's the question to ask.
So you're asking to...
So for example, imagine that IMF is universal. Then I would argue that it kind of goes into the direction that the binary distribution should be universal as well, and vice versa. If it varies, then what's the impact? Because the stars form together, right? So if they form binaries, then you observe it.
One of the challenges, as I'm sure most people listening are aware, is that if you have an unknown binary fraction and you assume one and you get it wrong, it has an impact on what you infer about the IMF shape. And so getting a good handle on how the binary fraction varies as a function of mass is actually quite important in knowing whether the IMF that you've inferred has the right slope or not. And I think that there's a lot of work that's being done to try and help nail that down. I'm very much aware of the BPAS models by Elridge and Stanway that I think in quite some detail try to implement and explore the impact of binaries in the stellar population synthesis environment. I think that that is one of the many areas that there is scope for a lot of developments and improvements in the way that we use population synthesis tools for understanding IMFs and galaxies.
Yeah, but one should not forget about the dynamics, because the binary is affected by that, so it's even more complicated.
Absolutely.
So at this point, since I think we can close, unfortunately, but we close it. I mean, it's been really, it went so quick, so fast. I'm really fascinating, and I would like to thank again Teresa and Andrew, because you made really an excellent dialogue today, duologue. Just to give you finally the final result for the moment, okay, for the our question, if our pool, whether the IMF is universal or not, we have still 11% of yes and 89% no. So there is a 1% more for yes. Okay, so still there is still open. Of course, that's to witness that it is still a big open question. So I really would like to thank you both once again, and I hope people. So I would like to remind to people that the talk will stay on this channel, so you can watch it again, and then you can also go to our webpage duo.eso.org, and then you can find also the link to the duologues of the previous two events, and plus this event, and then we will soon, if the speakers are fine, then we can also put the presentation. But this, let's see. But in general, also you can see the references there for related to the topic. And I would like to make the final. Maybe I can start. I can share very quickly. If I don't find my Zoom. I mean, I'm using so many monitors that I cannot. Here we are. Okay, let me share this. Okay, share. So I would like to just remind people that we do have now a program for the next events. Here, just a snapshot of the programs. So we will touch upon formation evolution of the solar system, then structural protoplanetary disks, and then dust-tied redshift. So a lot of, again, exciting topics. They are still available. The program is still available on our pages, and there we will put also the link to the YouTube channel. So with this, I would like to close. I will thank again Teresa and Andrew. Really, this was a big pleasure for me. I'm really honored to have seen your discussion today and your talk. I hope to see you live soon when condition will allow us to travel again. But we will continue this web format, because we think is a very nice platform to allow this level, a new creative way to allow this level of interactions and discussions. So thanks again. Thank you everyone for attending, and I wish you a pleasant day and see you next time. Thank you. Bye-bye.
Thanks.